The F-22N Sea Raptor was a proposed carrier-based version of the F-22 Raptor designed to bring stealth and supercruise performance to naval aviation. Conceived to replace aging carrier fighters and extend the defensive reach of fleets, it aimed to merge land-based stealth technology with ocean-based operations. This video examines how the concept originated, why it never reached production, and how its core design ideas continue to influence modern carrier programs, such as the F-35C and the upcoming F/A-XX. The F-22N Sea Raptor originated as an ambitious concept, adapting the Air Force's fifth-generation F-22 Raptor for maritime operations. In the early 1990s, as the F-14 Tomcat neared retirement, the U.S. Navy looked toward a future where stealth and speed would define carrier-based defense. The concept envisioned a jet that could protect carrier groups, intercept airborne threats far from the fleet, and provide early detection with advanced radar, all while operating safely from the tight, punishing confines of an aircraft carrier. The proposal drew from the existing F-22's advanced technology. The F-119 PW-100 turbofan engines would enable supercruise speeds above Mach 1.5 without afterburners. Its APG-77 ASA radar could track multiple targets at ranges approaching 400 kilometers, giving it the ability to detect and respond to potential threats long before they reached carrier airspace. Engineers also planned to expand internal fuel storage to increase range, an essential feature for long-distance maritime patrols. However, converting the Raptor into a carrier-ready jet meant more than adding a tailhook. The structure needed significant reinforcement to survive catapult launches and arrested landings. Folding wings were considered to conserve deck space, while a strengthened landing gear system was required to withstand the extreme impact loads of carrier landings. Some early concepts even explored variable sweep wings, borrowing from the F-14's design, to improve both low-speed control during deck approaches and high-speed stability in flight. Each proposed modification carried a cost, not just financially, but also technically. Every hinge, panel, and additional component risked increasing the radar signature or adding structural weight. Maintaining the F-22's seamless stealth profile while embedding moving parts for carrier operations would have been an extraordinary challenge. Still, the concept captured imaginations. A stealth aircraft capable of defending an entire carrier group autonomously promised a leap in survivability and awareness. The Sea Raptor could have acted as both a guardian and an information node, quietly patrolling beyond the radar horizon and feeding data back to the fleet. On paper, it looked like a technological masterpiece, a bridge between air dominance and naval resilience. Transforming a land-based stealth fighter into a carrier-capable one is among the most complex challenges in aerospace engineering. The F-22's lightweight titanium composite frame, designed for agility and stealth, was never built to endure the intense mechanical shocks of carrier catapults or arresting cables. Strengthening that frame meant adding bulk and reinforcing joints, immediately threatening the Raptor's delicate balance between weight, thrust, and maneuverability. Weight is a quiet killer in aircraft design. Each kilogram added requires more lift, which increases drag, which demands more fuel, which adds yet more weight. A vicious cycle. Heavier airframes also stress carrier elevators and deck systems, requiring structural adjustments on the ships themselves. Then came stealth integrity. The F-22's smooth, unbroken skin and precisely angled surfaces are what make it so hard to detect. Adding folding wings or variable geometry sections meant introducing gaps and seams that reflect radar energy. Engineers could theoretically use radar-absorbent coatings and tight tolerances to mitigate this, but maintenance at sea, under salt, humidity, and corrosion, makes perfection difficult to sustain. Protecting sensitive composites from saltwater exposure alone would have demanded extensive redesign and maintenance protocols. Fuel was another constraint. A heavier aircraft requires more energy to sustain flight, and carrier operations often mean extended patrols. Increasing fuel capacity would enlarge the fuselage or alter internal systems, risking the F-22's optimized aerodynamics. Even small modifications to intakes or weapons bays could compromise stealth or limit payload options. From a logistical standpoint, the costs became staggering. Lockheed Martin's preliminary estimates suggested that adapting the F-22 for naval service would double per unit production cost compared with the Air Force variant, and the Navy would need to redesign maintenance infrastructure and pilot training pipelines around a unique platform. In parallel, the F-35 Joint Strike Fighter program was gaining momentum, promising a single family of jets adaptable to air, sea, and vertical operations. Compared to the F-22N, the F-35C offered multi-role flexibility and shared technology across services at a fraction of the developmental risk. Ultimately, the Sea Raptor fell victim to physics, economics, and timing. Every enhancement to make it carrier-ready eroded what made the original Raptor special. By the late 1990s, the Navy officially shifted focus toward the F divided by a -18E divided by F Super Hornet and, later, the F-35C, closing the chapter on a jet that might have rewritten the rules of naval aviation had the math and materials allowed it. Even though the F-22N never left the drawing board, its ideas didn't disappear, they evolved. The Sea Raptor's guiding principles, stealth, speed, sensor fusion, and extended reach, became foundational for the future of carrier aviation. Modern programs like the F-35C and the upcoming F/A-XX borrow heavily from that same philosophy, aircraft that merge digital awareness with low observability to dominate complex airspaces. The F-22N's influence shows in how today's naval fighters act not just as aircraft, but as information hubs. The APG-77's conceptual radar range inspired next-generation sensors with greater bandwidth and network data sharing, paving the way for systems such as the distributed aperture system and advanced sensor fusion in the F-35C. Where the Sea Raptor might have been a lone hunter, the F-35C is a team player, linking ships, drones, and satellites into a single combat network. Design lessons were also carried forward. Engineers learned that navalization must be built in from the start, not added later. The F-22N's challenges demonstrated how adapting an existing design for carrier use multiplies engineering problems. This insight led the Navy to insist that future aircraft, like the F/A-XX, include carrier requirements from day one, avoiding costly retrofits that compromise stealth or handling. Conceptually, the Sea Raptor highlighted a strategic shift from raw platform dominance towards systems integration. It wasn't enough to have the fastest jet or the longest range. The new frontier was in connectivity, data fusion, and adaptability. The F-22N's unrealized architecture became a theoretical test case for how to merge stealth technology with carrier operations, influencing defense industry design logic long after the concept faded. The Sea Raptor also serves as a cautionary tale. Ambition alone can't overcome fundamental trade-offs between stealth, strength, and sustainability. Yet, its vision continues to inspire. Engineers working on the F/A-XX and emerging unmanned carrier aircraft often reference the Sea Raptor as an example of daring innovation that was technically ahead of its time. In the end, the F-22N Sea Raptor may never have flown, but its shadow stretches across every deck where stealth meets salt air. To dive deeper, don't forget to like, share, and subscribe. Thank you for watching. See you there.